again. So now we are going to start um, start graphing some of these transformations and see what is uh, what's going to happen when we do so. So, there's a couple of ways to go about this. Of course, you could take the easy route and use a graphing calculator, but we are hardened veterans of math, so we're not going to do that. What we're going to do is make some tables to show the relationship between the parent function and the transform function. So in this case, our function is f of x equals 2 to the x plus 5 power. That's going to be my table on the right. And on the table to the left, I'm just going to have the parent function 2 to the x power. So my x is going to be -2, -1, 0, 1, 2. And my f of x, well, we have graphed the parent function before. We know that it's 0.25, 0.5, 1, 2, 4. That was the first graph that we did in this unit. So now for the transformed function. Now, x plus 5. So think of it, we're taking each point on the graph and moving it to the left 5 spaces. So basically imagine, I was graphing -2 and 0.25. But I'm going to the left 5 spaces. So it's not -2 as my x value, it's -7. But I'm still keeping the same f of x value. Now -1 and 0.5 go to the left 5 spaces, you're at -6. But you still have that same f of x value. Instead of 0, we have -5, but we're still at 1. -4 will give us 2, and -3 will give us an f of x of 4. And you can always verify these for yourself, such as f of -3. Well, that's 2 to the -3 plus 5, which -3 plus 5 is 2. 2 squared is 4. It's easy to verify on your own. But now we can graph this function. So at -7, so 1, 2, 3, 4, 5, 6, 7, we're at 0.25. Then we're at a half. Then at -5, we're at 1. At -4, we're at 2. At -3, we're at 4. -1, we're going to be at, -2, we're going to be at 8. And this is our new function. So something that looks like this. Again, just shifted over 5 spaces to the left. Now, a lot of the same things are going to apply. Domain is still just all real numbers. Our range is still at y is greater than 0. As x approaches infinity, f of x does so as well. F of x is going up and up and up. As x approaches -infinity, it's still approaching 0. Our y-intercept, okay, so your y-intercept is the location in which your x value is 0. So if to determine where that is, just find f of 0. So that means I have 2 to the 0 plus 5 power which means I'm looking at 2 to the 5th power, which is 32. So my y-intercept is 0, 32. And my asymptote is still, as we can see, y equals 0. All right. That is it. I mean, that's very, I guess simple transformation we just did. Let's take a look at one other. That one's too easy. What's a cool one? Whoops. Yeah, let's do this one. This one might be one of the trickier ones. So, all right, make 2 tables. One for the parent function, one for the our actual function. I have my x's and my f of x and f of x. So same deal. On the left-hand side, I'll graph my parent function, or I'll plot out the parent function, which is 3 to the x power. And on f of x, over here on the right, it's going to be the whole 1/2 times 3 to the x power plus 1. So we graphed the parent function in the second video in this list. So that was -2, 0.1 repeating, -1 with 0.3 repeating, 0, 1, 1, 3, and 2, and 9. Now, how is this going to behave differently? Well, there's no... we're not messing with the exponent anyway. It's not like the last one where we had x plus 5. It's just we're still keeping the same x values. So -2, -1, 0, 1, and 2. If I was modifying that exponent in any way, then I'd worry about the x values. But now we don't really have to. So my y values. What's going on? What's going on there? So, well, we're taking our f of x values. Oh, well, think of it in terms of the transformation, right? We're stretching or compressing the graph by 1/2 and going up 1 on the y-axis. So, what can we do? How can we really figure out what's going on? I think it's a little bit easier to start out with like the whole numbers, like 9, for instance. Looking at 9, if I took half of 9, like the 9, I'm talking this right here. When x is 2, f of x is 9. Now to transform that, if I took half of 9, that would be 4.5. And if I added 1 to that, that would be 5.5. And that's the basic gist. If I have 1, 3, right? So I take half of 3, which is 1.5, and then add 1 to get 2.5. At f of x is 1, half of 1 is 1/2 plus 1 is 1.5. And then here it's going to get a little like, all right, like half of 0.33333 repeating plus 1. You can use a calculator for that because it's a little annoying to try to do in your head. It's about it's 1.16 repeating. And -2 is 1.05 repeating. So how does this look like when we graph it? Well, at -2, we are at 1.05, so just slightly above 1. And at -1, we're at 1.16, not much higher, but hey, I mean, whatever. 0, we're at 1.5. At 1, we are at 2.5. And at 2, we are at 5.5. So 1, 2, 3, 4, 5.5. So our graph is going to look something like this. As we can see, the rate of increase isn't as much, but it's still definitely increasing. Our domain is going to remain unaffected. It's still just all real numbers. The range, well, our minimum y value this time is 1. So my range is just y values that are greater than 1. Now our end behavior, as x approaches infinity, so does f of x. As you can see, the graph is still growing. But as x approaches negative infinity, f of x is approaching 1. See, if we look at y equals 1, like that point, our graph seems to be going in that direction. In fact, that's also our asymptote. As you can see, at the line y equals 1, the blue graph is definitely, it looks like it's on it just because, resolution and all that. The picture is not great, but it's definitely approaching that red line, but it's never going to quite hit it. So might as well get that way. Asymptote is y equals 1. And our y-intercept, well, we already have that on the graph. Our y-intercept is the coordinate 0, 1.5. So these are some examples of graphing function transformations. Quick couple to kind of know how to deal with them. Once you get handy with it, they're not so bad. Just make sure, keep track of what you're doing. Take it step by step, and you'll be fine.